Hello to everybody. We are starting our IAU Commission the Local Universe seminar, and today we will hear the presentation by Saroon Sasi from the University of Andres Bello in Chile. And we will hear about investigations of the Magellanic Cloud disk. So you are welcome, Saroon.
Yeah, thanks everyone. Thanks for giving me the opportunity. So today I'm going to present my work which I did as a research student in Indian Institute of Astrophysics, India. And the paper is already published, Saroon and Subramanian, 2022. So the title is Shape of the Outer Stellar Warp of the Large Magellanic Cloud Disk. Okay. So these are the contents. Like I will give an introduction about warps and the formation scenarios, and about Magellanic system, the motivation of our work, followed by data and analysis, results, and summary. Okay, coming to warps. Warps are vertical distortions of gaseous or stellar disk of galaxies. So mostly these are observed in disk galaxies, which are widely observed when they are viewed in edge-on. So there are basically three types of warp we commonly observe in these galaxies. The first one is the S-shaped warp, where both the outer edge is warped, but in opposite direction. So here it is warped, moving away from us, or warped up, and the other edges will be warped on the opposite side. And U-shaped warps, again, both sides are warped, but in the same direction, or more specifically, moving in a upward direction. And there are cases like L-shaped warp, where only one side of the galaxy is warped, the other side remain like a proper disk. Okay, these warps are actually prominent in H1 observations, and as I said, they are actually better observed when the galaxy is viewed H1. And stellar warps, of course, have smaller amplitude compared to the H1 warps, because H1 gas will be very extended out to larger radius and uh, larger away from the disk. Okay, so some of the warp formation scenarios include, so there are many theoretical possibilities or many observed possibilities of this warp formation scenario. Some of them are the intergalactic magnetic fields acting directly on the H1 gas in disk, which is proposed by Batten et al. 1990. And superposition of two or more non-symmetric S-shaped warps can also trigger the formation of a U-shaped warp. So this actually triggers the formation of a U-shaped warp. And tidal interaction by nearby companions can also induce a warp formation. It can be any shape, of course. And external stolls originating from the gravitational forces of a sinking satellite, and flyby encounters or multiple flyby encounters can also trigger a U-shaped warp formation or S-shaped warp formation. So we have warp formation mostly by tidal interactions or interaction with another galaxy or collisions. Okay, so in this context where the tidal interaction is very prominent in producing a warp, it will be better. It will always be interesting to look in the nearby companions, the Magellanic system. So talking about Magellanic system, they consist of the Large Magellanic Cloud here and the Small Magellanic Cloud, together known as the Magellanic Clouds. And they are actually an interacting pair of dwarf galaxies, which is also a satellite galaxy of Milky Way. Okay, first they were considered to be revolving around the Milky Way, or on their first passage around the Milky Way, or completed a multiple observation orbits around the Milky Way. It was considered first like that, but later the HST proper motion observations now suggest that they are on their first infall. And here we can see the radio data combined with the optical data of the Milky Way. So here the radio data maps the H1 region H1 gases, and it suggests that it is an interacting pair of system, and we can see signatures of interactions. Like here is the Magellanic Bridge that connects both the clouds, and this Magellanic Bridge is actually formed due to a recent collision between these Magellanic Clouds. And here we can see the Magellanic Stream and the leading arm. So there is of course influence of the Milky Way in forming these some of the features there might be, but since I said they are on their first infall towards the Milky Way, we can expect that most of the signatures are formed by the collision between Magellanic Clouds themselves. So in this context, actually, it will be interesting to look at one of the companion, the Large Magellanic Cloud, which is closer to us, to see whether it have a warp formation or it has a warp. So that's why we are looking into the Large Magellanic Cloud. So this is a disk galaxy with a planar geometry, and the orientation or the structural parameters of this galaxy can be defined based on the position angle and its inclination. So this has been done by previous authors, and they also noted that the inner disk of the galaxy is actually rippled structures, and there are distortions. But most of these studies actually were limited to the inner region of the LMC itself, because a larger data or a larger coverage, data covering or the entire LMC was not yet available. So they couldn't study the whole structure of the LMC as it's to conclude how the shape or what is actually causing these warps, etc. So the overall global shape of the warp was still a mystery. Okay, and what motivated us for this study is like, okay, first, Besla et al. 2012, actually, they predicted, they modeled the shape of the structure of the LMC, considering interaction with the SMC and with the Milky Way and all. And they found that from their model, it was found that the LMC shape would be warped. And in the southwestern part, it warps towards the SMC, owing to interaction with the SMC. Whereas on the northeastern part or the northern part, we can see it warps down, like in the opposite direction. And they suggested that this might be mostly due to interaction with the Milky Way. And a recent study by Choi et al. 2008, they used the optical data of SMASH from SMASH, Survey of Magellanic Stellar History. And they also used the red clump stars to trace the distances, and finally and they observed a warp in the southwestern part, which is consistent with what Besla tells. So this warp, this prominent warp is actually in the southwestern part, and it is owing to interaction with the Milky Way. And the study also suggests that this might be due to the recent collision between the LMC and SMC itself. But the survey was not able to cover the entire LMC again, and the northern part of the LMC remained unexplored. So again, now a global picture was not there. So we really don't know what exactly is happening here. So we were curious to explore this part of the LMC so that we will get an overall picture of the warps of the LMC to check whether it is consistent with the predictions of Besla et al. And also to verify the warp of the southwestern part. It was always better to look at the entire thing. Okay, so that was the aim of our study, to estimate the orientation parameters of the LMC covering the entire disk plane, and also to look for the presence or absence of a warp in the unexplored northeastern LMC disk. Okay, so for this, we need a data that covers the entire LMC and SMC, or the entire Magellanic Cloud. So for that, we have Gaia data. So Gaia have a large field, large coverage of the Magellanic Cloud, especially it was able to cover the entire Magellanic system. So we used the red clump data, data of red clump stars from the Gaia data, from the Gaia data, Gaia EDR3. But firstly, we started this project with actually EDR2, then came to EDR3. We were able to verify in both the data, the swaps and everything. Okay, so this picture shows our selection. Actually, we took a large area, like a 380 square degree of area, which is almost like 11 degree of the LMC, which covers the entire LMC disk and also the northern part, complete northern part also. And the red polygon, as you see, is the selection by SMASH. So they were only able to study this much region. Most of it was into the southern part. The northern part was really unexplored. So clearly you can see we are actually covering a lot of unexplored region in the northern part, especially in the northern part that SMASH couldn't access. So we expect to get an overall picture by this selection. So this was okay. But before selecting the data, we have also given some cuts in parameters in order to select a clean sample of the LMC. So we give a cut in parallax less than 0.2 milliarc second so that it will remove some of the foreground stars. And we give a cut in flux over error in all the Gaia magnitudes. And a proper motion cut was given based on the stellar density in that proper motion for the LMC. So we gave a cut like in RA, proper motion in RA between 1 milliarc second per year and 2.5. And in proper motion index, minus 0.8 and 1.5. So in this, when we plot the proper motion density, we will get the largest density in this area. So we chose that. And we also gave an astrometric excess noise less than 1.3 and RUWE less than 1.2. So this was based on the standard values obtained from the Gaia papers. Okay, so now we have the data. Now let's move on to the analysis. So for the analysis, what we did is we actually divided the entire region into small bins to analyze the to obtain the distances to these each of these bins. So we divided the regions based on a size. We divided this region based on size, which depends on the density. So in the inner regions of the LMC was so densely packed, so that we give a size of like 10 into 10 arcminic square boxes. And as we moved to the outskirts, we were forced to increase the size. We could have an adequate number of stars to visually identify the red clump region, because we are actually using the red clump stars as tracers. Okay, I forgot to tell you that just give an introduction. So red clump stars are actually used as standard candles, so we can trace for distances, and based on these distances, actually we are modeling the structure of the LMC. Okay, so we need distances to each of these bins. For that, we need to identify red clump stars in each of the regions. So for the same purpose, we have took a larger bin as we move to the outskirts where the density decreases, so that we were able to visually identify the red clump stars in each of these regions, so that it can be verified, like it is sure of them. Like taking a constant cut throughout the region, when it comes to the outskirts, we were not able to see enough stars so that a red clump region could be identified. Okay, so this is one of the sample region. So as you can see, Gaia is having only Gaia magnitude is limited to 20.5. So we have the RGB, and here we have the red clump region well defined. So what we did is we first give an initial selection box, a large selection box, and based on the errors in identifier, or the statistical errors, statistical standard errors, actually we identified in this large selection box, we give a 2 sigma cut in the standard errors to define another box which has a well-defined RC region selected. So in this way, we selected the red clump stars. So the first box was given visually, then we gave a cut 2 sigma box to redefine to select the red clump stars in a well-defined way. So this was our method of selecting the red clump stars. And so we calculate the mean magnitude of the or median magnitude of red clump stars in each of these regions. So in this way, we selected the RC stars in each of these subregions. All of these subregions, there were a total of 3,000 plus subregions were there. So we did visually verified the red clump region in each of the subregions and then calculated the median values in each of the subregions. And then, so now we have the median values or the absolute magnitude of RC stars in each of the subregions. Now, then we corrected it for extinction using Scronetal map to Scronetal 2020, the extinction maps proposed by Scronetal 2020. But this map was only up to some 5 to 5.5 degrees of the LMC region. And so that since we are covering a larger area, we used this for a latest extensions within the region available. And beyond that, we opted for Schlegel et al. 1998. So we compared both of these maps to correct for extinction. And so now we have the D-redden peak values of the RC median obtained for each of the subregions. And we also can calculate the relative distances to each of the subregions using the distance modulus equation, where the LMC center was taken as like 49.9 into 49.9 plus or minus 0.54 kiloparsec. Okay, so we have the D-redden peaks. We have calculated the distances. So, and we also know the RA deck of each of these, or the median RA deck of each of these subregions, which means the RA deck of these red clump stars. Okay, so then we converted this RA deck and D into X, Y, and Z using equations from Large Magellanic and Sioni. So basically, RA deck is converted to Cartesian coordinates. So now we have the X, Y, Z coordinates. And with this, we will be able to fit these coordinates or these RC stars into a plane using the equation AX plus BY plus CZ is equal to. So we defined a plane of the LMC using the equation, and we fitted this using we fitted the red clump stars to this plane. And then from this, we were able to calculate the orientation parameters, the inclination and the position angle of line of node. So inclination, okay, I'll come to the values. Also, we were able to analyze the radial dependence of this orientation parameters, and the dependence with stellar population effects was also studied. Okay, so this was the analysis where we studied the radial variation of the inclination and position angle. So here what we did is we divided the LMC into each annular regions or each circular regions, like from the center, like 1 degree to within 2 degree, that is like circular regions, which is given by the red lines, and the dashed dot lines is actually is the annular regions. So, but as you can see, up to 9 degree, we took an annular region of 1 degree each, but beyond 9, it was very sparsely populated. So we had to take from 9 to 11 degree as a whole to calculate the parameters. So what we did is we used the same method, calculated the orientation parameters in each of these annular and circular region, and then check the radial variation. And as you can see, for the circular region, the inclination seems to drop from a high value like 30 up to some 5 degree, and then stays like a constant. So this can be founded with the inclined bar of the LMC, because the bar of the LMC is actually not aligning with the disk, it is a bit more inclined. So this accounts for that. And the sudden variation in annular region at the outer part of the LMC disk can be accounted by the distortion of the LMC, or the LMC disk is actually perturbed in the outer part due to collisions and interactions, of course. And the same trend can be similar kind of trend can be seen in the position angle also. The outskirts is largely distorted, but these trends are, of course, not similar to what Choi et al. Did or what they did with smash data, because the position angle and or the structural parameters, the estimation of structural parameters is actually affected by the coverage of the data. So It does depend on the spatial coverage of the data that is also found by Smash et al. Smash also, the Choi et al. Also suggested that the orientation parameters of LMC disk can vary with the spatial coverage. So since they were having most data in the southern part, the orientation parameter can be less homogeneous. So we have an entire region, so it might vary, but we are having more consistent values in a sense. And from the structural parameters, we found that the inclination to be 23.67 degrees and position angle to be 158.91 degree. And this was actually consistent with the previous estimates. And we confirm, okay, I'll come to this. Okay, and okay, this is what we plotted actually. So the dashed line actually shows the LMC disk plane, the best fitted disk plane, and the median, the red line shows the median offset of distances of RC star in each region. So what here we can see is we can clearly see the southwestern warp. So of course we have confirmed the presence of the southwestern warp in the LMC as what is suggested by Choi et al. So it is moving away from us. But in the northeastern part, again, we also were able to identify a new warp. For the first time, we identified this warp, but Besla et al. Predicted that this was something going down towards us owing to interaction with the Milky Way. But what we found is something that is moving away from us, forming a U-shaped, asymmetric U-shaped warp. So this is what we were able to observe. So this might be due to, might suggest that the warp in this northeastern part can be also due to the effect of SMC-LMC interaction. And we found the amplitude of the warps, what we are getting is actually a bit lesser than what Choi et al. Observed. And this is due to the the stellar density as we move to the outskirts. So since we were taking larger bins in the outskirts, we might have got only a few points in the outskirts. So it cannot go beyond this. Okay. Now, okay, so we found the warps, U-shaped warps, but for this purpose, we have actually used the intrinsic RC magnitude to be a constant value throughout the LMC disk. So we also need to check whether it has any effect, check whether there is anything that is affecting the warp. The northeastern warp to be exact, because it is having an amplitude of 1.2 and the southwest we are getting an amplitude of 2.8. So if something happens, we have to check whether it has any effect due to the stellar population effects. It has anything to do with stellar population effect. So stellar population effect means we have to account for the variation of intrinsic RC magnitude throughout the LMC disk. So for this, we have calculated the gradient in RC magnitude in different radial bins. So what we did is we defined some radial bins. This was also following the method, following the analysis in Choi et al. So this was like we divided radial bins into 0 to 2.7 degree and 2.7 to 4 degree, 4 to 8.5 and beyond 8.5 degrees. So in these radial bins, we actually calculated the age and metallicities using age metallicity relation for LMC disk from the literatures. And from the age metallicities, we plotted the parsec isochrone and found out the parsec isochrone and found out the magnitude of the RC region, Rutland region. And we were able to observe that in the disk, the radial bin between 2.7 and 4 degrees actually 0.03 mag brighter than the inner region. So this was consistent with the observations of Choi et al. Also. And we were able to calculate a gradient of 0.021 mag per degree in between the radial bin 2.7 to 4 degree. And then 4.8 to 85 degree, we took a constant magnitude, constant RC magnitude, which is the RC magnitude at 4 degree. Like using this gradient, we will get a magnitude at 4 degree, and we use the same throughout 8.5 degree because there were not much change. And beyond 8 degree, we calculated a gradient of 0.53 mag per degree. But even while applying this gradients, the overall shape of the warp is unaffected. So we can say stellar population have some effect on the amplitude. There is a slight variation in the amplitude, but the overall shape is still U-shape. It is not the overall shape is not fading due to stellar population effect. So these are the summary, like using RC stars as traces, we estimated the structural parameters of the LMC disk, which is inclination to be 23.67 degree and position angle 150, almost 159 degrees, and which is really consistent with other analysis. But this is the structural parameters for an entire disk. So this is like a more global picture of the LMC, and we detected the warp identified by Choi et al. We also have a prominent amplitude also. It is up to like 3 kiloparsec. The warp extends up to like 3 kiloparsec. And for the first time, we detected a warp in the northeastern part of the outer LMC disk with an amplitude of 1.2 kiloparsec. And the northeastern warp, yeah, actually, as you can see in the figure, so the warp extends towards it comes down and launches from below the plane. It launches from below the best fit plane and it moves up. So this moving down of the warp can be accounted for the incursion of bar with different inclination. And since both the warps are twisted back in a direction away from us, we can say that the overall shape of the LMC warp is kind of an asymmetric U shape, not an S shape as suggested by as predicted by Bello et al. So this is kind of an observational constraint to the models predicting the LMC-SMC interactions. So that's it. Thanks.
So thank you very much. So the influence of the Small Magellanic Cloud is larger than of our galaxy, yes?
What?
So influence in appearing
yes,
of the...
exactly. Like it can be thought of like they are on their first infall towards our galaxy. And most of these properties are due to the influence of SMC, yes.
Okay, interesting. Do we have some questions? From participants of the seminar?
Yeah, I don't know where the stellar density in this region, sky region, but is there any problem in the contamination in the Gaia data?
Contamination?
In the measuring, to making.
Okay. I forgot to say. Like in the central part, it was too crowded. So it was very much crowded. So, but in these figures, actually, I forgot to tell that. So we have removed the inner 3 degrees so that we can remove the effects of the incursion of this inclined bar. So what we did is we removed the inner 3 degree and plotted. These plots are actually without the inner 3 degrees, so it will remove most of the contamination also. I think I have a plot on that. So this is kind of, when we include the inner 3 degree, this is kind of what we are getting. So the inside, there are large distortions, and this can be due to the crowding effect or maybe Gaia data problems, but still in the outer region, we could clearly see the U-shaped warp, of course, but this does not change the results, but we just removed the inner 3 degree to get these plots. Yeah, that was the problem, yes. And also in the outskirts, it was actually sparsely populated, so we were not able to get this much density as we moved to the outskirts. So it was not extending all the way like Smash, because Smash used like and the entire region was binned into 10 into 10 arc-minutes square, so that you can see a very high density for the warp. So it extends up to some 4 degree, but we were able to see it up to some 3 degree. But still this was like prominent feature in ours also. So we were able to define that.
Okay, thank you.
So do you think that this will be already the final results, or there could be some more observations and treatment?
Yeah, no,
Because
maybe we can check this in H1 map or H1 data, how extent the WAPs are. Maybe. And recently I read about a paper suggesting the northeastern structure of the LMC that also have a similar kind of origin, because I think I have the figure. So we have the warp identified somewhere around here. We have the spiral lamp here, so it is not associated with the spiral lamp. So we have the warp here, and they also found a northeastern structure, something like this. There's a gaseous structure, which is entirely different from the northeastern warp, but kind of having a similar origin. I don't know. We have to check that. That's in gaseous, but it's like a horizontal strip of gas, but which is mostly due to the influence of Milky Way. So Milky Way does have influence on the gaseous part of the LMC disk, but the stellar distortions in the stellar disk is actually affected by the southwestern one, because otherwise we were able to see an integral shaped warp, like S-shaped warp. But what we are observing is something interesting, something really different. So this can be due to multiple interaction with the SMC. By considering SMC in an elongated orbit around the LMC, you can say it might have flown past to the LMC multiple times. So like multiple flyby encounters, this might have created this warp. But now the recent results, like northeastern structure, is actually kind of making it more interesting, because it has influenced by the Milky Way, where the gaseous part is actually tidally stripped by the Milky Way, but not the northeastern warp. Yeah.
Okay, so thank you very much, Saroon, and we wish you to finish your PhD studies successfully and to give input to the investigations in future. So thank you.
Sure. Yes, thank you. Thanks. So bye-bye.